welcome back to my channel. This is part 2 of gradually varied flow topic. So I think in gradually varied flow, we have seen it is just a steady non-uniform flow whose depth varies gradually along the channel. So I think we mean GVF. So it is just gradually along the channel flow varies, or the depth of the flow will vary. So it involves what? The solution of the dynamic equation. Solution of dynamic equation. So we will solve the dynamic equation. So it is just a first order differential equation. So we will just calculate how the depth is changing with respect to distance or along the channel. So the main objective of GVF computations is just to determine the shape of the flow profile. The shape of the flow profile. So the flow computation is needed to analyze problems such as determination of the effect of hydraulic structure on the channel. So we will have effect on hydraulic structure. So flood may overtop over the bank of the channel. So it can just create erosion on the side of the channel, or sometimes damage to the structure. So we will just determine the effect on hydraulic structure of the channel, and also inundation due to a dam or weir construction. So this is also another aspect why we compute GVF computations. So under this topic, we will go through each step how we can calculate the length of gradually varied flow or backwater length. And the other thing is just estimation of flood zone. So in estimation of flood zone, sometimes errors may we may just commit an error in measurement of such discharge, stage discharge, something like that. So I think these are the main aspects why we just calculate the GVF profile. So I think next we can see this is the general equation, which is the GVF, which is the dynamic equation. dy by dx is equal to S naught minus SF divided by 1 minus full number square. So using this dynamic equation, I think we have seen in the previous part 1 how we can just derive this equation from total head. So we start from total head from two sections. We have energy and also potential head and also kinetic head. Then we have loss between the two. Then we derive this equation. So this is bed slope of the channel, and this is slope of energy line. Okay, so sometimes you may have such equation in terms of conveyance of the channel. So conveyance, we mean the carrying capacity of the channel. So you have S naught times 1 minus K naught over K the whole square, where K naught is just the conveyance at normal depth of the flow, and K is normal, just the depth, total depth of water, and 1 minus YC, which is critical depth, divided by Y, the whole cube. We will see with the example in detail, or sometimes we can use this equation, which is for wide channel, dy by dx S naught times 1 minus Y naught over Y, the whole 10 over 3, then 1 minus YC over Y, the whole cube. So we will see these formulas. So these are the methods of GVF computation. So broadly, there are 6 methods of gradually varied flow computation methods. So the first one is direct integration. So we will have integration, and then we will just calculate the length of backwater. And graphical method, also we have graphical method. We will just have some distance dx, and then we can calculate. And numerical method, also we will use numerical. And multiple integration method, also this is also important. We have direct step method and standard step method. And the fifth one is numerical or computer methods. We may have MathCAD and Excel and other computer programs we have. And Euler's method also we will use for just each step or dx step. We will have to calculate the depth of water. And Runge-Kutta method, of course, This is fourth order longitudinal method. So these are the methods to compute gradually varied flow profile. So let us see direct integration method. So differential equation of GVF is nothing, just it is non-linear first order ordinary differential equation. So I think we will have differential equation of GVF from the above equation, and then we have just different researchers have made attempts to integrate the GVF equation, and then we have to arrive up to the total length of water, which is going back from a weir or any control structure. And the method described here is just D2 which is based on certain assumptions. D2 we have certain assumptions. So by this method, the section factor and conveyance, section factor Z and the conveyance K are expressed in terms of the depth of the flow by introducing these exponents, M and N exponents. So this is the general equation for direct integration method. So we have to determine the conveyance of the channel, and then we have to calculate normal depths and depths of the flow. So let U, for example, Y over Yn, the above equation may be expressed for dx as dx if you just derive dx from the previous equation, from the general dynamic equation, we have this equation. Then Yn over S naught times 1 minus 1 over 1 minus U the power of n plus Yc over Yn the whole m, then U the power of n minus m over 1. So this expression is the general equation. So you can integrate now. Integrate both sides. You integrate both sides here and here. Once you integrate, then we have to calculate this equation. X will be this one. So this is just the length x of the flow profile. Then finally, you have just to add constant. So how do you determine U and N and M? So the first integration on the right side, which is the first integration on the right side of the above equation is designed for varied flow function f of un, or f of un is integration of u from 0 to u du over 1 minus u to the power of n, which is known as the varied flow function. So the second integral in the equation may also be expressed in the form of varied flow function. So the varied flow function v is equal to u to the power of n over j, and j is equal to this one, n over n minus m plus 1. So how do you compute this equation into other format? So let us see. Integral can be transformed into this one. So after transformation, you have integration u to the power of n minus m over 1 minus u to the power of m du. Then j over n, you have varied flow function, which is f of vj. Then this is just integration from 0 to v dv over 1 minus vj. So using the notation of for varied flow function, the equation can be written as this one. So this is just the equation. X is equal to a times u minus f of un plus vf, then vj plus constant. So where a is this one, then we may just apply. So you have j and n, m, etc. So we will calculate j and n and m, then finally we will substitute. So I think and f of un is and f of vj are varied flow functions. Then the length of the flow profile between two consecutive section 1 and 2. If you have two sections, for example, if you have such weir structure, then you may have just length of backwater curve due to the blockage up to some level. So you may have between 1 and 2. For example, if this is 2, then x2 minus x1. You will just subtract, then you get total length. So a times this value will give you just the length of the profile. So just it refers section 1 and section 2, 1 and 2. Then for varied flow function, make use of varied flow function table, which is given in just appendix D or Methods let me show you just this one, the computation of the flow profile by direct integration method. You have such thing, which is 1, 2, etc. column. Then you have y. Then you have to calculate u, v, f of un, f of vj, x, delta x, then total length. Then let me just show you the general approach, which is from let me show you from handout. This is the handout, so conveyance, you can just have conveyance q over square root of SF for gradually varied flow. For uniform flow, you will make this one S naught. And I think yeah, just this is just the equation after substitution. Then you have so I think we have table. This is a table, gradually varied flow computation f of un, varied flow function. You have u, n, and u. Then you will have just to read from this one. So once you read from this point of view, then you will just read from the center point, which is any number you can have in terms of f of un. F of un, you have to compute. We will see with the example actually, I hope. Okay, so the first step is determination of hydraulic exponent, which is the first hydraulic exponent, which is m. First, you have to determine m. What is m? For example, for rectangular channel, z square is equal to c1 y is the power of m from section factor formula, then a cube over t. Then once you have this one, then you have area of rectangle b cube y cube divided by b. Then you will cancel. So b square, you have c1 is b square, then m is this one. So instead of m, you have m3. Instead of m, you have 3. Then for triangular channel, the same, you will have m square over 2 for c1, then m will be 5. Just exponent, you can read this one. This is 5 instead of m. And for trapezoidal channel, again, you can determine, or you can plot z, which is section factor, versus y on log scale. Then if m is constant between 2 points z1 and y1 and z2, y2 in this plot, then you can have this equation to find m. If m is just difficult to calculate using this equation, you can use this one, 2 log of z2 over z1 log of y2 y1. But you have to have 2 points, z1 y1 and z2 y2. And the second one is determination of the hydraulic exponent n. How do you determine n? So this is just second hydraulic exponent n. So for wide rectangular channel, you have approximately hydraulic radius is approximately equal to the depth of the flow, and area is equal to b times y. Then k2 is equal to c2 y is the power of n. Then if you substitute here, then finally you can find 10 over 3 for wide channel. N is 10 over 3, which is 3.33. For triangular channel, you can check again. You will get this equation. So we have this general equation. You take this general equation, which is just k2 is equal to c2 y is the power of n. Then you will substitute the value for wide rectangular channel. After substitution, we will find this one. And for trapezoidal channel, just the minimum value of n is 2, which is up to n for deep rectangular, and maximum of n, this one for rectangular channel. Or you can plot of log k versus log y is prepared if n is constant between 2 points k1 y1 and k2 y2. Then finally in this plot, it is determined as n. N can be determined as 2 times log of k1 divided by k2 over log of y1, y2. So k first you have to determine, then finally you will just have some equation. So k is just covariance of this channel, and I think z is section factor. So the procedure of computation for direct integration method is first compute normal depths and critical depths. The first step, from the given data, which is discharge, Manning roughness, and bed slope, and determine the hydraulic exponent n and m for an estimated average depth of flow in the ridge under consideration. Then compute j. You will compute j. After you compute n and m, you will compute j. So j, once you compute j, compute the value of y divided by yn. So, and v is equal to u the power of n over j. So at two intersections of the ridge. So once you have y, depth of the flow, and normal depth of the flow also you have, then you will substitute. Then from the varied flow function table, you have just f of un, f of vj, f of un and f of vj, f of un and f of vj from the table. Then you will compute the length of the ridge by the general equation. Then you have this just f of un and vn. You can see this one. This is important. This is important. Then you can see just how to compute varied flow function f of un, and f of vj. You just have vj. So this is, I think, you can make vj. So u or v downward you read, then j or n you will read here. Then finally you will pick values from here. So if, for example, if you calculate un 3.2 and 0.4 for this one, for u, then you read this value. So I think you can read any number depending upon f of un, and f of vj, Okay, the second method is graphical integration method. So this method integrates the equation of gradually varied flow by graphical procedure. So we will determine just the gradually varied flow profile by graphical procedure. So once you have this equation, or general equation, which is dynamic equation, this is the general equation, dy by dx is equal to s naught minus acf over 1 minus flow square. Then you can make reciprocal, dx over dy will be this equation. Then integrate both sides again. Integrate both sides of the equation. So once you integrate both sides of the equation, just crisscross, then integrate both sides using this equation. Then you will have this equation. The length of the profile is x2 minus x1, because from 0 to x, then you may have x2 and x1. Then integrate y1 to y2. So you may have depths of the flow. For example, you may have like this. So this is, for example, y2. This is y2. Then here you may have some hydraulic structure here. Then this is y1. Then corresponding distance x2, x1. So the length of the profile will be 1 minus flow square over s naught minus sf, and dy will be this one. Dy, the change in depth, will be this one. So I think after integration, you will find this equation. Change in length, summation of change in length, each strip area will be summation of each delta x. So you have here each value. After you add all these strips, you can find the length of the profile. Clear? So for every length of you have the drop in water elevation. Clear? Water surface elevation dy. So you have just summation of dx over dy, which is the change in y. I, the first subscript, then the second. Summation of dx over dy, I plus 1 over 2. You have to take average of the two, then you have to take yi plus 1 minus yi. So the depth, the change in the depth, or you may have table. So for example, here if it is y, then for example here y1, y2, then just succeeding depths minus preceding depths, you can subtract. Then you have to divide this one by 2. Then finally you can find the length of the profile. So this is the format you are going to prepare a table. Y, you go down, y depths, you start from the hydraulic structure or control structure, maybe the initial depths, then it will go to the backward direction, flow is going to this direction, then you will take up to normal depths or up to the required depths, and area of the flow according to the channel cross section you can find, and V will be computed because discharge may be given. So V will be from continuity equation Q over area. Then perimeter of the cross section R, top dimension, Froude square, and SF Froude square. Actually, you know Froude square formula from the previous chapter. Froude square. Froude square you have Q square T over GA. Q square T over GA cube. Clear? GA cube. So using this equation, you can determine SF, slope of energy line. Also, you can have Manning equation or Cherchesy. dx by dy, you will have just to divide each. Then change in area. Then finally, x will be computed. Summation of this one. Cumulative will be taken from here to here. You go like this up to the final depths. So if you have summation of change in area or length will be summation of xi. Okay, so consider two channel sections at the distance x1 and x2, and with corresponding depths of flow y1 and y2. The distance along the channel is x, then you can have. So if a graph of y against f of y is plotted, which is y against f of y is plotted, then the area under the curve is equivalent to x. The value of the function f of y may be found by substitution of area. By substitution of area, p, and also s naught and sf. Just we have Manning equation for various values of y. For a given q, you can determine f of y. Then hence the distance x between the given depths y1 and y2 may be calculated using numerical integration or measured graphical integration. So this numerical or graphical method gives distance from the depths. Distance from the depths. So we will have example on this one. So this is I think the curve, or just how you can determine del x. You have this channel, then you may have discharge Q is going, then you will have energy line and water line, then finally you can just determine these all aspects. So you have yi plus 1, which is succeeding minus preceding. It goes on like that. So I think we will see this one with the example. So this is a graphical. So you have del x, strip distance between the two profiles. Okay, thanks for watching this video. If you have any question or doubt regarding this topic, please write down in the comment section below. I will reply on it. Thanks again.